Every successful application starts the same way. One server, one application, one database. No load balancers, no cache, no message queues, no microservices. And that's not bad architecture. In fact, it's exactly the architecture you should build. Because when you have only a few users, adding complex infrastructure doesn't make your application better. It only makes it more complicated. But success changes everything. More users arrive, traffic keeps growing, the server becomes busy, the database starts slowing down, requests begin waiting, users start seeing errors. Suddenly, the architecture that worked perfectly yesterday is no longer enough today. So what do engineers do next? Do they immediately move to microservices? Should they add Redis, Kafka, Kubernetes? Or is there a better way to evolve the architecture? In this video, we are going to answer that question by building a system together. We will start with a single server, and every time the system reaches its limit, we will solve that problem by introducing just one new architectural concept: load balancer, caching, read replicas, database sharding, CDN, message queues, microservices, API gateways. By the end of this video, you won't just recognize these components, you will understand why they exist, when you actually need them, and what problem they solve. Because great system design is not about memorizing architecture diagrams, it's about understanding why the architecture had to evolve. So let's start where every successful application begins, with a single server. This is our entire application. One application server, one database. Every request follows the same path. The user sends a request. The application processes the business logic. If it needs data, it reads or writes to the database. Then it returns the response back to the user. Simple, right? At this stage, this architecture is fast, easy to build, easy to deploy, and easy to maintain. In fact, many successful products start exactly like this. A common mistake developers make is thinking they need distributed systems from day one. They don't. A load balancer won't make a small application faster. A cache won't help if your database is not under pressure. Microservices will not solve problems you don't have it. Good architecture is not about adding more components. It's about solving today's problem with the simplest possible design. And right now, this architecture is doing exactly that. But as more users discover the application, the amount of work this single server has to do keeps increasing. Eventually, one server reaches its limit. So the first question every growing system asks is, can we simply make this server more powerful? The simplest solution is, don't change the architecture, just upgrade the server. Add more CPU, more memory, faster storage. This approach is called vertical scaling, or we can call scaling up. The application doesn't change, the database doesn't change, no new infrastructure is introduced. We simply move the application to a more powerful machine. For many systems, this is the first and right scaling decision. It's very quick, it's simple, and it immediately gives the application more capacity. But this solution has a limit. Every server has a maximum size. At some point, there is not a bigger machine to buy, and even if there is, it becomes significantly more expensive. There is another problem. We still have only one server. If that server goes down because of a hardware failure, an operating system issue, or a planned maintenance window, the entire application becomes unavailable. So we have increased the server capacity, but we have not improved the system's availability. We are still depending on a single machine, which leads to the next question. So instead of buying one bigger server, what if we add another one, then another and another? Now instead of one powerful machine doing all the work, multiple servers work together to handle incoming traffic. This approach is called horizontal scaling or scaling out. The biggest advantage is flexibility. As traffic grows, we can simply add more servers. If traffic decreases, we can remove them. Unlike vertical scaling, we are no longer limited by the size of a single machine, and because the application is running on multiple servers, the system is also more resilient. If one server fails, the others can continue serving users. Sounds perfect, right? Not quite. We have just introduced a new problem. A user opens the application. There are now 3 servers available. Which server should receive the request? Users can't decide that. browsers can't decide that. So we need something in front of our application that receives every request and intelligently distributes it across the available servers. That's where the load balancer comes in. A load balancer sits in front of your application. Instead of users connecting directly to your servers, every request first reaches the load balancer. Its job is simple: receive the request, choose a healthy server, forward the request, and return the response back to the user. Now users don't need to know how many servers are running, whether there are 3 servers or 300. The client still connects to a single endpoint. But here is an interesting question: how does the load balancer decide which server should handle the next request? There is not just one way. The simplest strategy is round robin. The first request goes to server 1, the second request goes to server 2, and then third will go to the server 3. Then the cycle repeats. This works well when all servers have similar capacity, but in production, servers are not always equal. Some servers may already be handling more active requests than others. In those situations, a strategy like least connection is often a better choice because it sends new requests to the server with the fewest active connections. Sometimes servers don't even have the same hardware. One server might have twice the CPU and memory of another. In that case, a weighted strategy allows more traffic to be routed to the more powerful server. Different applications use different routing strategies, but the goal is always the same: distribute traffic efficiently without overloading a single server. Now let's consider another situation. What happens if server 2 suddenly crashes? Without a load balancer, users would continue sending requests to that server and receive the errors. To prevent this, the load balancer continuously performs health checks. It periodically asks each server a simple question: are you healthy? As long as the server responds successfully, it continues receiving traffic. The moment a health check fails, the load balancer removes that server from rotation and automatically routes new requests to the remaining healthy servers. When the server recovers and starts passing health checks again, it is added back into the pool automatically. This is one of the key reasons why modern applications can continue serving users even when individual servers fail. So we have solved our traffic distribution problem. Users can now be served by any healthy server, but we have also introduced a new challenge. A user logs in, the login request is processed by server 1, and the user session is stored in that server's memory. A few seconds later, the user clicks My Orders. This time, the load balancer routes to the request to server 3. Server 3 has never seen this user before. It doesn't know the user is already logged in. The user may suddenly be asked to log in again. This happens because the application is stateful. Each server keeps user-specific information in its own memory that works with a single server, but once request can be routed to any server, it becomes a problem. The solution is to make the application stateless. Instead of storing user session information inside the application server, we store it in a shared location or send it with every request, such as using session store or JWT token. Now every server receives all the information it needs to process the request. It doesn't matter whether the request reaches server 1, server 2 or server 3. Every server behaves exactly the same. This gives us another important benefit. If a server crashes, we can simply replace it with a new one. No user session is lost because nothing important was stored inside the server. Now our application servers have become truly interchangeable, which raises another question. Traffic is not constant throughout the day. Sometimes we have 10 servers sitting idle. Other times even 20 servers are not enough. So instead of manually adding and removing servers, can the system scale automatically? Our application is now running on multiple stateless servers. Adding a new server is easy. Removing one is just as easy. But there is still one problem. Who decides when to add a new server? Imagine it's 2 a.m. Very few users are online. Running 20 application servers is simply wasting money. Now fast forward to 10 a.m. A marketing campaign starts. Traffic suddenly jumps from thousands of requests to hundreds of thousands. If we wait for an engineer to notice the problem, users will experience slow response before new servers are added. Instead, we let the system make that decision automatically. This is called auto scaling. Auto scaling continuously monitors the health and load of the application. Common metrics include CPU utilization, memory usage, request rate, or response time. When these metrics cross a defined threshold, new application servers are automatically created and added behind the load balancer. As traffic decreases, unnecessary servers are automatically removed. This gives us two major benefits. During peak traffic, the application gets the capacity it needs. During low traffic, we don't pay for servers that are not doing any work. Auto scaling works because our application is stateless. Every new server is identical. The load balancer simply starts routing requests to it. From the user's perspective, nothing changes. The application just continues working. So we have solved the application scaling problem, but another part of our architecture has not changed at all. No matter how many application servers we added, they all still connect to the same database, and sooner or later that database becomes the next bottleneck. So far our application has been using a single database, but before we think about scaling the database, we should first ask a more fundamental question. Is this the right type of database for our application? Not all data is the same. Our application stores users, orders, payments, bookings. These are business critical transactions. The data is related. It must be accurate, and multiple operations often needed to succeed together. This is where a SQL database is the right choice. It provides ACID transactions, strong consistency, and relationships between data. But every application also generates another type of data, which is user activity, application logs, product views, search histories, sessions. These records grow rapidly and don't require complex joins and are often accessed differently. For this type of workload, a NoSQL database can be a better choice because it's designed to scale horizontally and handle large volumes of semi-structured or unstructured data. Notice something important. This is not a choice between good and bad. It's about choosing the right tool for the right problem. In fact, many production systems use both a SQL database for transactional business data and one or more NoSQL databases or specialized workloads. We have chosen the right database, but choosing the right database doesn't automatically make queries fast. Imagine your orders table has just a few hundred records. Finding one order is easy. Now imagine the same table has 100 million orders. A user searches for order ID. Without an index, the database may have to scan row after row until it finds the matching record. As the table grows, queries become slower, response time increases, and every application server starts waiting for the database. The solution is not adding another database. The first solution is much simpler. Create an index. Think of an index like the index page of a book. If you want to find a topic, you don't read every page, you jump directly to the page number. A database index works the same way. Instead of scanning the entire table, the database can quickly locate the required rows. This dramatically improves the read performance. That's why indexes are commonly created on columns used in where, join, order by, and group by queries. But indexes are not free. Every time data is inserted, updated, or deleted, the index also needs to be updated. Too many indexes can slow down write operations and consume additional storage. So the goal is not to index every column, it is to index the column that your application queries most frequently. Even with proper indexing, every request still reaches the database. Now think about your application. How often do users request the same data? Popular products, flight routes, hotel details, application settings, user profiles. Thousands of users may be requesting exactly the same information. If the data has not changed, why should the database execute the same query over and over again? Instead, we introduce a cache. A cache sits between the application and the database. When the application needs data, it first checks the cache. If the data is already available, it's written immediately. This is called a cache hit. The database is not involved at all. If the data is not found, it's called a cache miss. The application reads the data from the database, returns it to the user, and stores a copy in the cache for future requests. This simple idea can dramatically reduce database load and improve response time because most requests are served directly from memory instead of querying the database. But caching introduces a new challenge. What happens when the data changes? If the database is updated, but the cache still contains the old value, users may receive stale data. That's why production systems need a cache invalidation strategy, such as updating or removing the cached data whenever the underlying data changes. So caching is not just about making application faster, it's about reducing unnecessary work for the database. And once the database is no longer busy serving a repeated reads, the next challenge becomes obvious. What if the number of read requests keep growing even after caching? Caching has significantly reduced the load on our database, but not every request can be served from the cache. Some data changes frequently, some queries are too dynamic to cache, and some requests simply require fresh data from the database. As the application continues to grow, millions of users are still reading data every day. The problem is every read request is going to the same database. Soon, the database spends most of its time answering read queries instead of processing important business transactions. The solution is to separate reads from writes. We keep one primary database responsible for all write operations like creating orders, updating users, and processing payments. Then we create one or more read replicas by continuously replicating data from the primary database. Now the application sends all write operations to the primary database while read requests can be distributed across multiple read replicas. This greatly increases read capacity without changing the application logic. It's a common approach in production systems where reads are much higher than writes. However, read replicas come with one important trade-off. Replication is not always instantaneous. There may be a small delay before the latest data reaches every replica. This is called replication lag. For most read operations, this delay is acceptable, but for operations that require the most up-to-date data, the application should still read from the primary database. Read replicas solved our read scalability problem, but they don't help with write scalability. Every new order, every payment, every booking still goes to the same primary database. As the application grows, write traffic keeps increasing. The database becomes larger, indexes becomes bigger, backups take longer, maintenance becomes more difficult. Eventually, we have reached the limit of what a single database can handle. Instead of storing all the data in one database, we split into multiple smaller databases. This approach is called database sharding. Each shard stores only a portion of the data. For example, users might be distributed based on user ID. Customers with IDs 1 to 1 million are stored in shard 1, 1 million to 2 million in shard 2, and so on. Now, instead of one database handling every request, the workload is distributed across multiple databases. Each shard stores less data, processes fewer queries, and can scale independently. But there is one important question. When a request arrives, how does the application know which shard contains the data? The answer is a shard key. The shard key determines where the data is stored and where future requests should be routed. Choosing the right shard key is one of the most important design decisions because changing it later can be extremely difficult. Sharding gives us massive scalability, but it also introduces a new challenge. Cross-shard queries become more complex. Rebalancing data requires careful planning, and managing multiple databases is more operationally expensive than managing one. That's why sharding is usually the last step in database scaling. First optimize queries, then add index, then introduce caching, then read replicas. Only when those approaches are no longer enough, we have now scaled our application and our data layer.